Hello, my name is Apollo Schooler, and I'll be going over part one of the project. So we chose question one because out of the two, it just seemed easier, especially with the help of what we're involving some of it with is Studio Week 4, which helped with a lot of this question here. So it reads as, a box of mass big M is positioned at an edge of the frictionless turntable of radius r that is rotating at a constant angular speed. An ideal string passing over a massless pulley and through the hole in the middle, the table connects the box to a hollow ball of mass little m and radius little r with the string wrapped many times around the edge of the ball. Determine the angular speed of the turntable. So what do we have and what do we want to solve? We're given big M, which is the mass of the box, big R, which is the radius of the table, little m, which is the mass of the ball, and little r, which is the radius of the ball. We want to solve for omega, which is the angular speed of the table. Now we have a few assumptions going into this problem. We have frictionless contacts, infinite wind up and spool down. We weren't given a height, so we're just assuming that the ball has pretty much infinite string to go down infinitely. And we have an ideal string. It's near the surface of Earth, meaning we have uniform acceleration. We decide a moment of inertia for the hollow sphere, which is I equals 2/3 mr squared. The objects are ideal. There's a uniform circular motion of the disk. There's no air resistance, and there's no mass for the string. Now we move on lastly to our diagrams, which just shows the extended part of like what's going on with the equation. We have our Fg, Fn on the box. We have f of t affecting both big M and little m, Fg affecting little m. I decided to include a little diagram of like the torque going into the hollow ball and the mass being distributed since the middle is hollow, so it'd be more mass on the outside. And I also have the top-down view of the turntable, which shows the radius and the tension of the string, followed by the torque of it. And now we'll move on with Milo with part two.
All right, hello all, welcome to the calculation section of our project. To start off, we're going to want to keep in mind that let's say this object here, the block, is going to be moving with some angular velocity in this direction at the same speed as the disk. Essentially, like, although they are frictionless with respect to one another, they are moving in tandem in terms of their rotational kinematics. As a result, if they are moving with a constant angular velocity, they are going to obey the rules of uniform circular motion. Moving forward, we want to make sure we keep our definitions of the net torque as a vector, whereas one is equal to the inertia of an object times its angular acceleration. This can be rewritten as the net torque is also equal to the cross product between a net force acting on an object and the displacement of that force from the center of rotation given by the radius. For the purposes of this project, we define the moment of inertia for a hollow sphere to be 2/3 times the mass of the hollow sphere times its radius squared. We will want to keep in mind our rules for linear motion and linear forces, where we know that the F net is equal to mass times acceleration. This can also be described as the sum of all forces acting on the system is also going to be the net force acting on the system. Because we again are dealing with uniform circular motion, we can define the force of centripetal to be the mass times the radius of an object from the axis of rotation times the angular momentum of that object, which again is constant throughout its rotation. This, of course, being basically a breakdown of the angular acceleration being equal to the radius times the angular velocity squared, and then plugging that into F equals ma, this being an equation derived from uniform circular motion. We'll also want to keep in mind for uniform circular motion that the angular acceleration is equal to the tangential acceleration of an object in rotation divided by its radius from its center of rotation. Moving straight off the bat, we can start by looking at the ball's free body diagram, where we notice that the force of tension acting on this ball is displaced by some radius from its unspooling axis of rotation. As a result, we can write that the net torque equal to cross product of those two, of the radius vector and then the force vector acting on that object. We also know that the moment of inertia for this hollow sphere is given as such. And as such, we can write an equation as this: moment of inertia times its angular acceleration. For the purposes of this project, we could analyze how these torque vectors are moving in terms of their rotation and their direction of these torque vectors. But actually what we can do is something even more unique. Because the net force is only the one we observed is the force of tension, and the moment of inertia, the angular acceleration, is as such as we defined, these net torques are going to be exactly the same, and as such their magnitudes are also going to be exactly the same. As such, we can go about solving for the force of tension in terms of its magnitude, which we'll apply later in the problem to find other forces via pulley systems. As a result, we'll only be dealing with the magnitudes of these vector quantities when we set these equations equal to each other and solve for that force of tension. I've rewritten our angular acceleration in terms of linear translational acceleration, and we can go ahead and solve for the magnitude of the force of tension. Now that we have that, we still don't know what the tangential acceleration of this spool object is, but we can go ahead and solve for it and plug this back in to solve for the force of tension. We can do this by realizing that even though this force of tension on the object is displaced by some radius, where this is a free body diagram of the instance, where we have the force of tension acting on this object and the force of gravity where the center of mass is located towards the center of the sphere. Even though these forces are displaced and we would expect a rotation, rotational kinematics happen independently of translational kinematics in this specific context. There's no rolling, there's only an object unspooling over time. As a result, if we looked at it from a translational acceleration perspective or a translational force perspective, you can say that there is a force of tension acting on a point mass object and a force of gravity on that object as well. As a result, we can solve for the linear acceleration of the object by applying physics 212 concepts where we are dealing with the net force in an object, solving for the mass times acceleration, and going from there. We can apply the same logic for this object. Before we do that, we should define an axis of movement. We're expecting this object to accelerate downward, as again it is going to unspool over time and gravity is going to take hold of it, is likely going to unfurl like a ball of yarn. As a result, I want to define my positive axis of movement to be in the downward direction or towards the force of gravity, and as such, we can then find the sum of all translational forces on this object. Right. We have a negative force of tension, a positive force of gravity, which are written in terms of mass times gravity, and this is all going to be equal to the mass times acceleration of that object. We then go ahead and solve for acceleration, and then once we solve for that tangential acceleration or that translational acceleration, we can plug that back in to our equation for the force of tension on that object and solve for the force of tension in terms of the variables we've been given. And I'll go ahead and do that for you now. Now we're solving for the force of tension. We have now solved for the force of tension acting on this spooled object in a linear sense. As a result, we can now apply this back into our system and solve for further values. Now, when looking at this object from a top-down perspective, you have this mass that is rotating on a disk, right? And it's moving with a constant angular velocity. As such, there must be some centripetal force that is holding that object towards the center as it rotates along that disk. As a result, we can take a look at a free body diagram of this mass block. We have a normal force, right? We also have a force of gravity acting on this object occurring near the surface of the Earth. If we're not expecting the object to move up or down on this disk, those forces must be the same and is what we expect. And there also is a force of tension on that object that is pointing towards the center of the axis of rotation on that disk. If we first take a look at that, we immediately recognize that the only force on this object that is going to be supplying that centripetal force is going to be that force of tension. And if we solve for that force of tension, we can plug that into our equation for the centripetal force because they're exactly the same, and solve for the angular acceleration of this block, which in turn is also the angular velocity of the disk if they are moving in tandem with one another. So, going forward from there, we can apply our physics 211 concept of massless pulley systems, where if you have a mass here and you have a mass here, acceleration of the system, we know that if this pulley is massless, the force of tension on each of these objects is exactly the same. This is because you have Newton's third law pairs, this acting on the rope acting on the rope acting on itself. These forces then must also be the same if there's no moment of inertia generated by this mass of the pulley. As such, if we know the force of tension generated by this hollow sphere, we also know the force of tension acting on this larger block. And as a result, we can straight up say, okay, the force of tension on this block is this. We said before, if we solve for that force of tension, we know the force of centripetal force that is holding that object in a centripetal acceleration, and we can then solve for omega as a result. And then plugging all of that mathematical awesomeness together, we get 2/5. Again, we're saying that the force of centripetal motion is equal to the force of tension on that block. We have the force of tension, which we solved for before, and we set that equal to the mass of the object, which we know is big M, its radius from the axis of rotation, which we know is r, and then we don't know the angular velocity, which is what we're trying to solve for. Now we have everything in terms of the variables we've been given. We can then solve for the angular velocity of the mass block, which also in turn solves for the angular velocity of the disk. And that, my friends, is how you solve for the angular velocity of the system, and that is the equation in terms of the given variables that we've been supplied for this problem. Thank you very much.
Alright, now for the sense making. First of all, the units for our answer. We got omega equals the square root of 2 times the mass of the ball times gravity over 5 times the mass of the block times the radius of the turntable. And this gives that omega equals kilograms times meters per second squared over kilograms times meters, which would be the square root of 1 over second squared, or just 1 over seconds, which is the correct unit for angular velocity in base SI units. Now, if our symbolic answers make physical sense, we have 4 variables in our answer. Let's start with the mass of the ball, lowercase m, and gravity. For these variables, when m or g increase, the angular velocity also increases, as shown by this graph. This makes sense because as the mass of the ball or gravity increase, the tension in the string will increase because there's more force pulling the ball downwards. This means that the string will pull the brick inwards with more force so the table can rotate faster without the block falling off. Now we also have the variables capital M for mass of the brick and R for radius of the table, which do the opposite by decreasing the angular velocity when they increase. Now this also makes sense because centrifugal force equals the mass times the radius times the angular velocity squared. And the higher the mass of the radius of the block, the more force it requires to stay moving in a circle, or the slower it rotates with the same force. Now, after looking at how the variables affect the equation, let's look at a special case. For this special case, we set the mass of the ball to 0, and we find that with the equation, the angular velocity is also 0. For this, the ball doesn't have mass, and therefore doesn't provide any force of tension on the string. It follows from this that the brick has no inward force, and so would slide off the turntable if it was rotating. So, the lack of angular velocity is logical in this special case. Now I'm going to talk about our reflection. Alright, I thought this problem we solved was kind of like a combination of Homework 3 Activity 3 and the Spool of String Pulley activity in Studio on November 26th. The Homework 3 Activity 3 was about a mass on a string attached to a pulley and pulling on a block that was on a surface. This was similar to the problem in that we had to find the tension of the string and take into account the angular motion of objects, but different in that the rotating pulley with mass was what rotated instead of the attached object being free to rotate. The studio on the 26th involved looking at how 2 spools of string fell when tied to each other and with the string over a pulley. This was similar because we had a falling object that both created tension from its mass and gravity, as well as rotated and changed the tension with that rotation. The difference is that there were 2 objects falling instead of 1, and for this problem we needed to find the tension it would produce with an essentially fixed endpoint for the string.